Interesting. Okay, I'm gonna go with continue recording there. Sorry guys, I'm having some issues with Zoom. Give me just 1 second here. I think everything should be working. Can you guys hear me okay? Is anybody having a hard time hearing? All right, awesome. Okay, so today we're gonna pick up where we left off last week. Talking about inverse functions. There's a handful of other details related to inverse functions that we need to cover. There's all sorts of kind of cool relationships between a function and its inverse that I'd like to discuss, but we have to get through the nuts and bolts of it. We've got a fair number of metaphors and ways of understanding this. I'm going to give you just 1 or 2 more of those today, and then we're going to talk about algebraically how it is we can go about finding the inverse of a function. So without further ado, let's get to it. This is MAC1105, section 007. It's a lecture. Today it's what, the 23rd, I think? Yeah, 23rd. Today we're going to talk more about inverse functions. And if there's time, we might start talking about exponential functions, because that is the next topic. So maybe we'll introduce those. I did get a notice from one of you saying that that they weren't able to get into the exam 2 reflections. I did try to open those up. I'm guessing that it's some sort of complication with the DLP, because this is something that the math department Canvas is like pushing to all the other Canvases. Canvas courses, it might be a little bit complicated, but the exam 2 reflection will be open soon. I just have to call IT and see what the conflict is. So we did get permission to do this, but for some reason it's still not showing up. So exam 2 reflections. Should be open today. I just got to call IT. I saw your email earlier. And just like with exam 1, the exam 2 reflection, if you complete it, will earn you your 3% bonus on the exam grade. Okay. So I'm going to say recall. Given a function f, the inverse mapping is the relation that sends all of the outputs from f back to the inputs from which they came. Sort of the easy way to think about this, i.e., if f of a is equal to b, then a is equal to f inverse of b. And remember, this notation has nothing to do with multiplication. This is not f times a, it's f of a, right? So like this is, you're feeding the input a to the function f, and it spits out b. So just like how with the squaring function, f of 2 is 4, so 2 would be f inverse of 4. That's the sort of idea here. And there are ways to think about this that involve mapping diagrams, right? You can have something, where you reverse the arrows. And the sort of last thing we said in class, we saw that the relation f inverse is a function if and only if the original function f is 1-to-1, i.e., meaning passes the horizontal line test. So this is the stuff that we've more or less said so far. There are some other details, there are some other pictures, but I don't want to go through all of those things. So if you need a little reminder, just take a look at last Thursday's video that's been up since Thursday afternoon. But that's the basic idea. We had machine diagrams, and we talked about how the F inverse machine is just the F machine running backwards. We had mapping diagrams, and we talked about how F inverse is just what you get when you reverse the arrows on the original mapping diagram. Today, I want to talk a little bit about kind of verbal descriptions of functions. So remember, we had a bunch of ways of describing functions at the beginning of the class. You can have a graph, you can have a table, you can have algebra, and you can have a verbal description of a function. And this leads to a kind of cute analogy called socks and shoes. And I promise this will be the last little cutesy analogy I give you before we talk about how to solve algebraically for the inverse function. I haven't done it yet this morning. I'm still barefoot, so I can't show you. But normally in class at this point, I would sit up on the table and say, what is the inverse of putting on your socks and shoes? I'll address the question in chat in just a second. So Mark has a good question in chat about combinations of functions. I'll come back to that in just a sec. But think along with me for a second. In the morning, when you get dressed, you put on your socks and then you put on your shoes. Right? So think of a function. Let's phrase this as a question. What is the inverse of put on socks and shoes? There is an important thing here, so please don't dismiss this entirely. I know it seems like it's a cutesy thing that doesn't have anything to do with mathematics, but I assure you it does. When you wake up in the morning and you want to go somewhere, in order to get your feet ready to travel, you put on your socks and shoes. And there's an order to it, right? As you get dressed, the socks go on first, and then the shoes go on. If you want to undo that, you have to take the shoes off first, and then take the socks off first. So the original, as you put on socks, then put on shoes. The inverse has you doing the opposite of each of these things and in the opposite order, meaning you have to take off the shoes first, then take off the socks. You can't take off your socks before you take off your shoes because the shoes go over the socks. The same thing is true for mathematical functions. If you have a mathematical function that multiplies by 5 and then adds 7, that you want to undo, the order that you undo those operations to get the inverse function matters. So let me show you how this carries over into a mathematical example. Okay, so this is still socks and shoes stuff, but now we're going to look at a mathematical example where we apply the socks and shoes principle. Let's find the inverse x of the function f of x equals 2x minus 7. To do this, we're going to give a verbal description of this function. It's going to have a few different things that it does to its input in a specific order. And then we're going to talk about how to undo that following this socks and shoes principle. The original takes x and multiplies by 2, then subtracts 7. So thinking in this way, put on socks, put on shoes, would have an inverse take off socks, take off shoes. What would the inverse function do here? The original multiplies by 2, then subtracts 7. So we need to undo each of these operations. To undo the subtract 7, you add 7. To undo multiply by 2, you divide by 2. So the two operations that are going to go down here are going to be divide by 2 and add 7. But in what order? Good, right? We have to reverse each operation and we have to do them in reverse order. So what Logan said in chat is exactly correct. First, we're going to add 7, then divide by 2. So now that I have this verbal description of the inverse, can we describe that algebraically? Well, let's think. What is the function that does this? Adds 7 to its input, then divides that result by 2. What does that look like? F inverse of x takes x and adds 7. So that's x plus 7. And then it divides that whole thing by 2. And I hope you see that this is different than what you would get if you divided by 2 and then added 7. So this socks and shoes analogy is surprisingly powerful, surprisingly powerful. And you have some problems in your homework that ask you to do precisely this. They give you the original function verbally, and then they ask you to construct the inverse verbally. And I think even one of them then asks you to give an algebraic representation of the inverse that you constructed verbally. Any questions on this? Oh. Sorry, that's my little brother. He lives out in the Denver area. With the shooting at King Supers, I wanted to check in with him and make sure he's okay. I do want to look at one or two homework problems where you have to construct an inverse function, just to make sure we're all on the same page. The way we ended up doing this, I did also get an email from somebody asking to when would I be extending the homeworks. So homework 15, which is on one-to-one functions and their inverses, I extended that to this Thursday, no, to next Tuesday. But I would like you to try and finish it by this Thursday. I didn't want to mess up our routine. Your homework always comes due on Tuesday at the start of class. That's the normal thing. So homework 14 came due today. Homework 15, which we opened last week, but because we didn't get to finish, we wanted to talk a little bit more. I'm extending that to next Tuesday along with quiz 5. So you have until next Tuesday to complete homework 15 and quiz 5. But please try to get them done this Thursday. That way you don't fall behind, because we are going to start talking about exponential functions. This is going to open up today. And I want you guys to be in front of the wave, not falling behind it. But let's take a look at one or two problems here where you have to construct an inverse function. I'll go ahead and launch this. I've got one example in mind that I'd like to do before we look at these, but then we'll... Okay, so before we look at that, I want to just tell you how you find an inverse algebraically, because you don't always want to do this, right? You don't always want to take the time to write out the words, multiply by 2, then subtract 7. Okay, reversing those and doing them in reverse order, we could add 7 and divide by 2. This is fine, this works great. But it can be a little bit clunky, right? Because if someone gives you the problem in terms of algebra, it would be nice to have an algebra process that just gives you the inverse instead of having to kind of go through this verbal description along the way. So the above procedure for finding a verbal description of F inverse from a verbal description of F works. But to find F inverse algebraically, we do the following. And if you've learned this elsewhere in high school or in a previous algebra class, they may have taught you some of these things in a slightly different order. I want to really strongly encourage you to do it the way I'm about to show you. First, you write y in place of f of x. Two, you solve for x in terms of y. Three, you need to be mindful of any domain issues in your solution. And then lastly, you swap x and y. And I know that some of these algorithms, or sometimes when people teach this algorithm, they tell you to swap x and y first. Please don't do that. This is what I mean when I say some of these things are in different order than you may have seen before. There's a very good reason to save swapping x and y for the end. And it has to do with restricting domains. You see, not all functions are one-to-one. We've learned that. However, if you're given a function that is not one-to-one, you can restrict its domain. You can chop off part of the graph. And then what's left over, if you chop cleverly, will be one-to-one. And that is what I mean by domain issues. See, sometimes we need to restrict the domain of a function in order to make it one-to-one. And then when you go about solving for x in terms of y, there will occasionally be algebra steps where you need to think about the domain restriction that you chose. namely when taking square roots, things like that. So let me pull up your homework here and we'll find an example where this is relevant. Maybe first we should do an easy example and then. Well, they may have taken all those out. That's interesting. Okay. So let's do an easy example and then a slightly more challenging example. The example we had to begin with (2x minus 7). Yeah. Let's see if we can find the inverse algebraically instead of going through that verbal process. So remember our steps. First, we write y in place of f of x. So for this function, that looks like this. Y equals 2x minus 7. Then we solve for x in terms of y. So I'm going to take this equation right here, and I'm going to solve it for x. That means I want to get this x alone. So I need to undo all the operations on the right-hand side that are affecting x. First, I'll add the 7 over. So I'm beginning with y equals 2x minus 7. And then my very first step is to add 7 to both sides. That'll give me y plus 7 equals 2x. And then my second step in solving for x would be to divide both sides by 2. That'll give me y plus 7 over 2 equals x. And now I have x alone on the right-hand side. So I have completed step 2. I have solved for x. Third, I need to be mindful of any domain restrictions. Any domain issues? Well, I know what the graph of this function looks like. The graph of the original, 2x minus 7, is a line with slope 2 and y-intercept 7. That looks like this. This function is one-to-one. I don't have to restrict the domain, right? No matter where you draw a horizontal line here, it'll hit this graph at most once. So there were no domain issues. So we don't have to worry about anything here. And then our last step is to swap x and y. So I take this expression right here and I swap x and y. So that means I get x plus 7 over 2 equals y. And now this is f inverse. So f inverse of x is x plus 7 over 2. And that's what we found going through this process verbally. Right? When we wrote down the verbal description of the original, used the socks and shoes principle to find the inverse of that function, and then wrote down the algebraic description of the inverse that we had verbally, we got this same thing. And this might look like it's more complicated, like it takes longer, but for a more complex function, this is really the way to go. You don't want to have to go through that verbal thing every single time, especially if you have like a big polynomial or something a little bit more intimidating. Now, looking through your homework, it looks like we've actually chosen to remove all the problems that have potential domain issues. So I don't want you to stress too much about step 3 here, but I do want you to be mindful of it, especially if you intend to take pre-calculus, because in pre-calculus and in trig, we have very serious domain issues that you need to be mindful of as you invert those functions. But it looks like we've removed those from the college algebra homework set, so I think you might not need to worry about them here. I'll look into that. But I would like to look at one example where there is a domain issue, just to show you what I mean. So we're going to look at one more example here. Yeah. So this is a really good thing. Precisely what you're asking about, Mark, is what I want to address here. So what if your original function has like an x squared in it or something like that? The good news is that procedure I gave you, that 4-step procedure, is still going to work. We're going to get an inverse here. The bad news is that there is a non-trivial thing going on in step 3. So let's just dive in. First, we're going to write y for f of x. So that would look like y equals x squared plus 1. And then we're going to try to solve for x. So here I would subtract the 1 over, giving me y minus 1 equals x squared. And then I would take square roots on both sides, and that'll give me plus and minus the square root of y minus 1 equals x. And it's at this stage where I now need to ask, are there domain issues? And the answer here is yes. Remember, your horizontal line test is the key to figuring out whether this function is nicely invertible. It's precisely that that's going to tell you whether you have domain issues. So when you get to step 3 here, this is when you should graph this function. Now you should all know how to graph x squared plus 1 by hand, because it's a quadratic, and we've talked a lot about that. But if you're feeling insecure, if you're unsure, it's never a bad idea to take a look at the graph in the graphing calculator. So let's go ahead and throw this into the graphing calculator and see what we get. X squared plus 1. And I hit graph. And there it is. It's a parabola. It opens up because the lead coefficient is positive. Its vertex is at 0, 1. And you can see that because this is already in vertex form. So is this a one-to-one function? Yes or no? Somebody tell me, is this function one-to-one? No, it's not. Good, because there's lots of horizontal lines, right, that hit this function's graph more than once. This fails. Let me draw in a horizontal line here. So this fails a horizontal line test. And that's what tells us there are domain issues. So f of x, the original, is not 1-to-1 unless we restrict its domain. So what do I mean by restrict the domain? Well, remember, the domain is the set of all inputs, the set of all x values that are on this graph. If I throw away half of that shit, for example, throw away all the x values that are less than 0, then this whole piece of the graph will vanish. So if I restrict the domain, for example, to the interval 0 to infinity, like this, then that will be 1-to-1. This is what you get when you restrict the domain. I've restricted the domain to this interval, right? Which is this interval of x values over here. So I'm going to hold on to all of this stuff, but I'm going to throw away all of this stuff. The piece over here on its own is 1-to-1. Right, that piece which corresponds to this subset of the natural domain, that is 1-to-1. Why does that matter? Well, first off, we know that only 1-to-1 functions have inverses, which are themselves functions, and we really want our inverse to be a function. In terms of the algebra, if you look at this step, this is where we're at in our algebra process, solving for the inverse. You'll see there's this plus and minus over here. So right now, what we're saying is x is equal to 1 of plus or minus the square root of y minus 1. The x values that we've chosen to restrict to are positive numbers. And here we have x equals either some positive shit or some negative shit. So corresponding to our domain restriction, we take the positive square root of y minus 1 to be equal to x. And this is why you save swapping x and y for the end. If you had already swapped x and y, this would be a y and these would be x's. So it wouldn't be immediately obvious that, oh, the x values are positive. So, oh, this x value needs to be positive. And trust me when I say it can get substantially more complicated. So you really do want to wait to swap x and y till the end, because having not swapped x and y at this stage helps me match up the x values that I should be choosing from here, choose the plus or choose the minus, corresponding to my choice of domain restriction. You see, I could have chosen to throw the other half away. I could have chosen to stick with this. And then I would need to take the negatives here because my x's would all have to be negative because I would have thrown away all the positive x's. So now I know that this is the algebraic representation I want. And the positive here corresponds to the positive values of x that I should have because I've restricted my domain. And now we swap x and y. And that will give us the square root of x minus 1 equals y. So f inverse of x is the square root of x minus 1. And this is how you find domains algebraically. I know that this can seem a little bit intimidating at first, so I want you guys to take a second and make sure this is nice and clear in your notes, and share with me any thoughts or questions you have.
Yes, I have a question.
Please.
Okay, so we can find a inverse of any function, correct?
Yes.
Okay, so the reason why we're doing all this domain restriction is to ensure that the inverse that we're finding is a one-to-one relationship.
Not necessarily. So we're doing this domain, we can find the inverse of any function, but that inverse wouldn't be a function itself unless the original function is one-to-one. So if you have a non-one-to-one function and you want to look at its inverse, that inverse won't be a function unless you restrict the domain of the original function to make it one-to-one. So there's a few ways to say this. If you require the inverse to be a function, then the only functions which can be inverted are one-to-one functions. Another way to say this is you can always construct the inverse of a function, but that inverse will not itself be a function unless the original is one-to-one. Does that answer the question?
I'm still processing it.
So allow me to show you some pictures. The example we've just looked at, the decimals, because I think I'll be able to graph a little faster in here. If we start solving for the inverse, we actually get these two things.
Oh, yeah, okay.
So the two blue graphs together would be the full inverse relation. But notice that the blue graphs on their own are not, this is not a function, right? This fails the vertical line test. So in order to make the blue thing a function, I need to throw away half of it. And that would be the half corresponding to the left half of this parabola. So if I restrict the original red function's domain like this, then this is a one-to-one function, and the inverse of this one-to-one function is this, which is also a function. But if I don't restrict the red's domain, then the inverse is all of this blue stuff. And this blue stuff over here is not a function because it fails the vertical line test. For example, it sends the input 4 to two different outputs, right? Or it sends the input 5 to two different outputs. That would not be okay. So in order to get the blue to be a function, in order to throw away this bottom half, I need to throw away this left half. Right, exactly. So you can always construct the inverse relation. You can always turn the arrows around and point them backwards, send all the outputs back to the inputs from which they came. But if the original function is not one-to-one, then that inverse relation will not be a function. And since we want our inverse to be a function, we require that the original be one-to-one. And in order to make the original one-to-one, we have to restrict the domain. We have to throw away part of the graph. I know that this part of the graph is messing up the one-to-oneness. So I just throw it away. the tool we use to throw away the left half of that graph is called a domain restriction. So instead of letting the domain here be all real numbers, I just say I'm going to restrict the domain to the non-negative real numbers. That is, I'm going to hold on to only this right piece of the graph. And now this function, the restricted version of the original, is 1-to-1. And so it does have an inverse, which is a function, namely this. And if you chose the other domain restriction, you would get the other half of the inverse thing. You would get the negative here, which is the other blue. So if we chose to do this the other way, if I chose to restrict like that, this is 1-to-1, and its inverse would be this. You may notice some symmetries in those graphs, and the next thing I want to talk about is those symmetries. But before I move on, I want to make sure we're comfy with what's going on here. So are there any other questions or comments, concerns? Whatever's on your mind, I'd love to hear it. Okay, sounds like we're either quiet or comfortable, either one. So I want to talk about the symmetries that you see in the graphs of f and f inverse. This will be the last thing we say about inverse functions. So facts about inverses. First, f inverse of x is not the same as 1/f of x. I want to get that out of the way first. Inverse is not the same as reciprocal. It's a common misconception, and I see where it comes from. The notation here, this looks like a power, right? But it's not a power. These two things are totally different animals. And that's why you always hear me use the word reciprocal for things like 1/2. It's the reciprocal of 2, not the inverse of 2. So make sure this is clear, right? The inverse of x squared is not 1/x squared. It's the square root of x. Second, graphs of f of x and f inverse of x are symmetric about the line y equals x. So let me return to the example we were just looking at. I'm going to turn all this stuff off for just a second, and I'm going to add in the line y equals x. Put it here in green and dashed, so you know it's just for reference. The restriction we chose here was really this. So here was my original in that last one, right? This was x squared plus 1. And here's its inverse. You see the symmetry about this line? If I take a point on the graph of the original and I reflect it over this line, I get a point that's on the graph of the inverse. Right? Like if I take the point 1, 2 on the original, then the point 2, 1 is going to be on the inverse. Does everybody see it? You flip the point over the line y equals x, and you get a point on the graph of the inverse. If you take the point 2, 5 on the original, and you reflect it over the line y equals x, that gives you the point 5, comma 2. That will be a point that's on the inverse. So there is this line of symmetry. What this means is if you know the graph of f, you can sketch the graph of f inverse. If you know the graph of f inverse, you can sketch the graph of f. You just have to reflect the whole graph over the line y equals x. So you take this whole graph, you look at this line, and point by point, you reflect it over that line. That will give you the graph of f inverse. So for example, if I came in here and I told you the graph of the original looks like this, then you could draw the graph of the inverse by sketching in the line y equals x, and reflecting the original graph over this line. So if I reflect this, it looks like this. If I reflect this, I get a point here. If I reflect this, I get a point here. If I reflect this, I get a point here. There's always this symmetry between the graph of f and its inverse. Pretty cool stuff. Another way of saying the thing above is that if a comma b is on the graph of f of x, then the point b comma a is on the graph of f inverse of x. These two statements, the symmetry statement and this statement, are actually equivalent to one another. And there's a third way to think about it. I mentioned it earlier. If f of a is equal to b, then f inverse of b is equal to a. In other words, inputs for f are outputs for f inverse, and outputs for f are inputs for f inverse. And one consequence of this, and this is the last thing I'll say here, is that the domain of f is equal to the range of f inverse and the range of f is equal to the domain of f inverse. And these things right here, each of these little bullet points, makes for a wonderful true, false, or multiple choice exam question. So please make sure you remember these things. Each of these things tells you something really important about inverse functions. Some of them are even full characterizations of the inverse function. And each of these would make a really good exam question. You can bet that at least one of these, maybe more, will show up as questions on exam 2. I get a lot of people asking, how do I study for the true false? How do I study for the multiple choice? Because they seem to be a little bit conceptual and a little bit tricky. This is how, all right? You need to really internalize these things. And the way you do that is by looking at a lot of graphs, playing around with these things. But straight up, here are the facts you need. All right, if you remember these facts, then you will nail the true, false, and multiple choice regarding inverse functions. These things are connected to each other. All right, like if over here, I have the point 2, 6, that means over here, I have to have the point 6, 2. And it will be the point symmetric over the line y equals x. Because when you flip 2 points over when you flip a point over the line y equals x, that's what that does, is it swaps the x's and the y's. There are other consequences of this. For example, the y-intercept here, maybe this y-intercept is 0, 1. That tells me immediately that the x-intercept here has to be 1, 0. Or that there's a horizontal asymptote over here, tells me that there has to be a vertical asymptote here. Right, so all of these things, not only are they worth knowing in the raw, you should be thinking about the consequences of them as well. Okay. Let's look at one more homework problem from this set. Oops, please don't go away. Close. Oh, it looks like it might have. Okay, let me send it. What homework problem would you guys like to see for our last example here related to inverse functions? Is there a particular homework problem that we've been finding challenging? And if there isn't a particular one that you guys want to do, I will grab one. How about this one? How about number 17? Let's work through number 17 together. I think we've done an example with a table yet. Okay. So they give us a table for f of x. The table for f of x is simple. Just has a few entries, 0, 1, and 2 for the x values, and 0, 1, and 4 for the outputs. 0, 1, and 4. So we want to find a table for F inverse. We want to state the domains in range of both F and F inverse. Remember what the inverse does. So one way of reading this table, we can say from the table, we see that F of 0 is 0. F of 1 is 1, because when x is 1, f of x is 1. And f of 2 is 4. This means that f sends the input 0 to the output 0, sends the input 1 to the output 1, and sends the input 2 to the output 4. So this tells us that f inverse of 0 is 0. This tells us that f inverse of 1 is 1. And this tells us that f inverse of 4 is 2. Right? You just swap the inputs and the outputs. Now for the first two guys, the input and the output are the same. But for this last guy, you got to be a little bit mindful. The output is 4, the input is 2. F sends 2 to 4. So F inverse has to send 4 back to 2. And now here I can construct my table for F inverse. The inputs for F inverse are 0, 1, and 4. F inverse of 0 is 0. So when x is equal to 0, F inverse of x is equal to 0. F inverse of 1 is 1. So when x is equal to 1, F inverse of x is equal to 1. And F inverse of 4 is 2. So when x is equal to 4, F inverse of x is equal to 2. And you can see what happened between the tables, right? You just swapped the input and output rows. The inputs for the original are the outputs for the inverse. The outputs for the original are the inputs for the inverse. So boom, this is your table for F inverse. The last things we wanted to do are state the domain and range for each. So the domain of the original is the set of all the inputs for the original. It's just 0, 1, and 2. And remember how we write a set. It's curly braces. There's just these three things in there. There's no intervals, so you don't need interval notation. There's only three things, 0, 1, and 2. The range of the original is the set of all the outputs for the original function. That is 0, 1, and 4. The domain of F inverse, we can read from the table for F inverse. It's the set of inputs for F inverse, which is 0, 1, and 4. And the range of F inverse is the set of outputs for F inverse. That's 0, 1, and 2. Right? 0, 1, and 2. And what you notice is that the domain of F and the range of F inverse are the same. The range of F and the domain of F inverse are the same. Any questions about this? Okay. So I think that's everything that we really have to say about inverse functions. We should be feeling, oh, yep, let me see what we got there. So there's a question in the chat. Sure, sure, sure. Yeah, no problem. No problem. There is just one more thing that I'd like to say about inverses before we move away from this. And this is an alternate definition of the inverse function. It's the definition that in a slightly more grown-up math class we would use. And it also shows how these connect to the idea of function composition. So an alternate domain definition of inverse function. The definition that we use makes great intuitive sense. And it allows us to work directly with the objects and find the inverses because we understand that we're just trying to undo everything the original function does. I want you to think very carefully about what each of these things should be. And the first step to figuring out what anything like this is, as we said many times in class last week, is to write down what this means. This would be f inverse of f of x. And this one would be f of f inverse of x. I want to focus on the top. If I start with some number and I apply the function f to that number, f does something to x. Maybe it multiplies by 7. Maybe it squares it. Maybe it, draws a smiley face on it. F inverse should undo whatever it is that f does. That's the definition of f inverse that we've been using, right? F inverse is the function that exactly undoes whatever f does. So what should f inverse of f of x be? If I take x and I do something to it, and then I undo that thing, what should I get out? The original, yeah, the original what? What is the original thing here? What do we mean? You're correct, Kendra. I just want to go a little further. So if I take x, I do something to it, and then I exactly undo that thing, I should get back not f of x. F of x is what we get after doing the thing to x. Yeah, just x itself, right? So think of x as the bare feet. I put on my socks and shoes, and then I take off my shoes and socks. I get my bare feet back. Or think of x as a number, right? I multiply that number by 5, and then I divide that by 5. I should get the original number back. So x is the thing that's getting shit done to it. F does something to x, and then f inverse undoes that thing. So we should get back the thing we started with, which is just x. So Kendra, I think you're on the right track. It's just a matter of the language, the original what? The original input, not the original function. So the original input is x. F does something to it, does something to x, and then f inverse undoes whatever it is that f did to x. So if you start with X, do something to X, and then undo that thing, you should get X back. And the same is true in the other order. If I start with something, I do the inverse of an operation, and then I apply the original version of that operation, I should get X back as well. So some people take this to be the definition of the inverse function. For example, in calculus and in pre-calculus classes, we take this to be the definition of the inverse function. It's mostly useful when checking if something is or is not an inverse, but I just wanted to show it to you. I don't think you have any problems in your homework, again, that exactly force you to use this definition, but it's good to be mindful of it. For example, you have a few problems where knowing this can make your life considerably easier. And this will be the last time I pull this up here today, and we'll move on. I'll come back over here for anybody who still needs to write all those loads. Son of a bitch, come on. Come on, Pearson. There you go. I know you could do it. Yeah, so for example, down here in number 16, they ask us to use the graph to evaluate the expression f inverse of f of 2. Well, based on this definition, you know that f inverse of f of 2 should be 2. All right, so some questions can be answered more quickly if you are mindful of the other definitions. In other words, the inverse of a function is the inverse operation with respect to the composition operator. Right? Remember when I said early on that we were studying algebras of functions and we're interested in operations on functions? If you're considering this operation on functions, then the inverse function is kind of the thing that undoes the original function under the composition operator. So for example, if 7 is in the domain of f of x, then find f inverse of f of 7. Well, and this is simple because f inverse undoes f inverse of f of 7 would just be 7. That's the idea. F of x sends 7 to some number, but then f inverse sends that number back to 7. You don't even need to know what f of 7 is to answer this question. And we could write this in the circle notation if we wanted to. If the question asked what is f inverse circ f of 7, the answer would be the same. Inverse circ f of 7 is 7. Okay. This is all I have to say on inverses, but it's been quite a lot, right? We've had 2 lectures on this now. We've had a bunch of different ways to think about it: machine diagrams, mapping diagrams, algebra stuff, graph symmetries, all of that. And it's a lot to internalize. But I need you to take your time with this homework and make sure you really understand the questions that are in it, because the next thing we're going to learn about are exponential functions. Those aren't too bad, and they don't immediately have anything to do with inverses. After we learn about exponentials, though, we're going to start learning about logarithms. And logarithms, believe me, are the biggest headache in this class. I remember when I was learning logarithms for the first time, it absolutely blew my mind, and it was a real struggle at first. And I think most people find that to be the same thing. Logarithms are the inverses of exponential functions. So if you understand inverses well, and you understand exponential functions well, then and only then will you be a master of logarithms. And that's really what you need. Are there any other questions or comments or things we would like to address relating to inverse functions before we move on to introduce exponentials? Questions, they can be comments, they can be anything at all. Okay. So again, homework 15 and quiz 5, homework 15 and quiz 5 are extended through to the 30th, which is next Tuesday. But please try to finish them by, which is next Tuesday, but please try to finish them by this Thursday. I don't want anybody to fall behind. And the material we're about to start and we'll be covering for the next week or so is pretty challenging stuff. We're going to meet a whole new family of functions. So far, we're going to begin now an intro to exponential functions. I'll take just a few minutes on this and then I'll let you guys go. So far, we've talked about, or we've worked with linear functions, quadratic functions, linear functions are things, right, like ax plus b or mx plus b. Quadratic functions are like ax squared plus bx plus c. We talked about higher order polynomials, higher degree polynomials, rational functions, and power functions. Some examples of each of these, a linear function is like, 2x plus 3. Quadratic function is like x squared minus 7x plus 4. Higher degree polynomials can be something like 3x to the 4 minus 7x plus 12 or whatever. Rational functions were things like x minus 5 over x plus 1. And power functions could be all sorts of weird things. Could just be like x or 2x or the square root of x or 1 over x squared. Things where you really just have a constant times some power of x. And you'd be forgiven for thinking that all of these families together are getting pretty close to like all the possible functions. If you're allowed to do any sort of polynomial or any sort of rational function or any sort of power function, you might think that this is pretty much everything, but we're missing two hugely important families of functions. What do you notice? How do I say this? Everywhere there is an exponent here, the exponent is constant. None of these have a variable in the exponent. And there are some hugely important functions in mathematics which do have variables in the exponent. Imagine you want a function that doubles every time x goes up by 1. Imagine the doubling function. So f of 0, maybe that's 1. F of 1 should be twice as big, so that's 2. F of 2 should be twice as big again, so that would be 4. F of 3 would be twice as big again, that would be 8. F of 4 would be twice as big again, which would be 16, and so on. So what does this function do? It doubles the output every time x goes up by 1. You just multiply by 2. These functions are a big deal in nature. Imagine you're counting the number of bacteria after a certain number of hours or days. If this bacteria doubles every hour, each bacterium splits into 2, then a function like this is exactly what you need to keep track of the number of bacteria in your sample. These are called exponential functions. Functions which do this, and it doesn't have to be a doubling, but functions which do this sort of thing are called exponential. The example here is f of x equals 2 to the x. And the big change is that you have a variable in the exponent. Everywhere up here, this is x to the 1/2. This is x to the -2. This is 2x to the 1. The power is always a constant. Here, the power, the exponent, is a variable. And that's a big change. And you get a whole different family of functions out of this. Their graphs have their own sort of shapes. They're very different from polynomials or rational functions or anything else. And they're hugely important in science, physics, biology, everywhere. So the next few weeks, we're going to be studying these functions, exponential functions, and their inverses, which are called logarithm functions. I'm going to go ahead and open up the first homework on exponential functions today, and it's going to be due next Tuesday, along with homework 15 on inverses and quiz 5. Those have been open since last Tuesday, so you guys can get in there and work on those. If you haven't finished those yet, please do so immediately. And as you work through the homework on inverse functions, make sure you're taking your time to really understand them. But that is it. Any questions from me before I let you guys go for today? Alrighty then, on Thursday, we're going to take our first deep look at exponential functions, and that will be the end of the week. We are getting close to exam 3 already. I know that might be pretty surprising. So just keep a heads up for that. If you have any questions, come see me in office hours or send me a message on Canvas. Always happy to talk. Otherwise, just keep up with that homework, and I'll see you on Thursday. Bye, guys.